Okay, we're going to solve some specific examples of second order linear equations with constant coefficients using the method of finding the polynomial associated with them instead of going through turning it into a first order system. So here's our first one. The second derivative of y with respect to time plus 4 times the first derivative of y with respect to time minus 5 times y is equal to 0 with initial conditions that at time 0 y is equal to 11 and at time 0 the derivative of y is equal to negative 7. Okay, so as we said before, we can form a polynomial based on this by guessing that the answer is going to look like e to the lambda t. So the polynomial we'll get, as we outlined before, is lambda squared plus 4 lambda minus 5 is equal to 0. And that factors simply into lambda plus 5 times lambda minus 1. So our eigenvalues are lambda being 1 and negative 5. So that means our solution, y of t, is going to be some combination of e to the t. That's with lambda equals 1. We'll call that k1 times e to the t. And plus some other constant, k2, times e to the negative 5t. Now to figure out what these constants, k1 and k2 are, we have to go back to our initial conditions. We know that at time 0 we get 11, so that means that k1 plus k2 must be 11. But we also need to use this second condition, and to do that we need to take the derivative of y. So y prime is going to be k1 e to the t minus 5 k2 e to the minus 5t. So setting time to be 0, we get the following system. 11 is equal to k1 plus k2, and negative 7 is equal to k1 minus 5 k2. We have two equations, two unknowns. We're able to solve this. Subtract the second equation from the first equation to get 18 is equal to negative 6, positive 6, k2. And that implies that k2 is equal to 3, and therefore k1 is equal to 5. And so our solution, our specific solution in this situation then, is 5 e to the t plus 3 e to the negative 5t. And that's our solution. Okay, let's do another one. This time, we're going to have the second derivative of y with respect to time plus 4 times the first derivative of y with respect to time plus 20y is equal to 0. And the initial conditions are at time 0, y is equal to 2. And at time 0, the derivative of y is equal to negative 8. Okay, so again, we make our polynomial. This is going to be lambda squared plus 4 lambda plus 20 equals 0. Looking at this for a moment, we're just not seeing anything that's going to factor really well. 2 times 10 isn't going to work. 4 times 5 isn't going to work. Not looking pretty good. So we're going to have to use the quadratic equation, or rather the quadratic formula. And we get negative 4 plus or minus the square root of 16 minus 4 times 20, which is 80, divided by 2. 16 minus 80 is negative 64, so this gives us a negative 2 plus or minus 4i once we simplify everything. So we have complex eigenvalue here. So what that means is that our solution is going to be some combination of e to the negative 2t times cosine of 4t. This is negative 2t because the real part of the eigenvalue is negative 2. And we have the 4t in the cosine because the imaginary part of the eigenvalue is 4. And then we need a little bit of sine as well. So we're going to have e to the negative 2t sine of 4t. And we're going to have two constants, constant 1 and constant 2. And now we have our general solution, so we need to find our specific solution with our y at 0 and y prime at negative 8. Now note that this second term here has a sign in it, and so at times 0, it is not going to matter. So at times 0, this part is 0, so that immediately implies that k2 is equal to 2. That k1 is equal to 2. Okay, so then we can figure out what the derivative of y is. K1 is equal to 2, so we're going to have, let's see, the derivative, we're going to get negative 4 e to the negative 2t cosine 4t. Then, of course, we're going to have to use the product rule, and we're going to get negative 8 e to the negative 2t sine 4t. Now we're looking at the second part here. We have minus 2k2 e to the negative 2t sine 4t plus 4k2 e to the negative 2t cosine 4t. Okay, we have to use the product rule on each of these. We have to separate the e to the negative 2t and the cosine 4t and the e to the negative 2t and sine 4t. That's why we had to have such a complicated derivative there. Now, remember, just as before, we're plugging in 0, right? We're plugging in 0 into the derivative, so terms with sine are not going to matter. And so what do we get? We get negative 4 let's see, plus 4k2 is equal to negative 8. So that means k2 must be equal to negative 1. So we have our solution. Y of t is equal to 2 e to the negative 2t cosine 4t minus e to the negative 2t sine 4t. Okay, so that's our second problem. And let's do one more. For this one, our equation is going to be the second derivative of y with respect to time minus 4 times the first derivative of y with respect to time plus 4 y is equal to 0. And our initial condition will be at time 0, y is 1, and at time 0, the derivative of y is also equal to 1. All right, so the polynomial involved here is going to be lambda squared minus 4 lambda plus 4 equals 0. And of course, this factors lambda minus 2, squared equals 0. So we have lambda equals 2 is the only eigenvalue. And you recall, for systems, having just one eigenvalue leads to a slightly complicated situation. And when you follow that through with just this approach, you'll get the following general solution. Y of t is equal to k1 e to the 2t plus k2 t e to the 2t. Right? Recall, when you have only one eigenvalue, a repeated eigenvalue, you have this t times e to the lambda t term as well that you have to deal with. Now, at time 0, y is equal to 1. So note that this part is equal to 0 at time 0 automatically. So that immediately gives us that k1 is equal to 1. Now we do have to calculate the derivative in order to figure out what k2 is. So y prime is equal to 2 e to the 2t. I've already substituted 1 in for k1 plus k2 e to the 2t plus 2 k2 t e to the 2t. Now we're plugging in times 0, so this term doesn't matter. And we have 1, which is supposed to be the derivative at time 0, is equal to 2 plus k2. So that means that k2 must be equal to minus 1. So our solution is e to the 2t minus t e to the 2t. So those are 3 different examples of solving a second-order linear equation with constant coefficients.